before going into this present theorem called torricelli's theorem, let me remind you quickly what do you mean by Bernoulli's theorem is. I have proved it earlier in the other video. You can look for it in the playlist. But just for the sake of reference, I am telling you that for an incompressible, non-viscous, streamlined fluid flow, the sum of pressure energy, that is P by rho, potential energy, that is GH, and kinetic energy V1 square by 2 or V square by 2 GH1 is constant between 2 points of a fluid, that is P2 by rho GH2 and V2 square by 2. Their sum is always constant for a given mass, per unit mass. The sum of potential energy, pressure energy and kinetic energy per unit mass is constant for a incompressible, non-viscous, streamlined fluid flow. Taking that into consideration, let me tell you what do you mean by velocity of efflux is. We would like to derive an equation for velocity of efflux. What do you mean by that? Let us try to find out first, right? So let us consider a big vessel like this, filled with a fluid like this. Let this fluid is filled up to a height capital H. We are assuming it, right? Here we are having a small opening to this vessel through which this fluid comes out. It comes out with a certain velocity, and that velocity is called velocity of efflux, and we want to calculate that velocity itself. Let this small hole is at a height h from the top. So from the bottom, as the total height is h, it will be at a height of capital H minus small h. So let us consider 2 points in our journey. One point is here. Another point is at the exit of that liquid, the opening point, right? So I need to apply Bernoulli's theorem at these 2 points. If you call this point as one point, this is another point. Between these 2 points, I would like to apply Bernoulli's theorem. Because this is open to atmosphere, here the pressure is P naught. Here also we are considering a point when the fluid just came out of that small opening. So that is also open to atmosphere. So that's also having a pressure P naught. This point, with reference to this point, potential energy is always measured from a reference point, is at a height h. Whereas the other point is at a height of h minus h from a reference. At this point, let the velocity is v1. At this point, outer exit velocity is v2. Let's apply Bernoulli's theorem as we are talking about. In the place of p1 and p2, both are open to atmosphere. Therefore, p naught by rho plus g. H of that point, with reference to this point, is capital H. Velocity is v1 square by 2. Now let's come to this second point. Here also the exit point you're talking about, it's not a point inside the vessel, it's about a point that came out of the vessel. So P naught by rho plus G. Height is H minus H and velocity is V2 square by 2. So P naught by rho's will be cancelled at both these points. Right? And look about velocities. Look at this velocities. Here, this is area A1. Here, this is area A2. It's very clear from the diagram that A1 is much bigger than A. Isn't it? A1 means the open area. A2 means area of this small opening. As per equation of continuity that we have learned, A1 V1 equal to A2. As A is inversely proportional to V, AV equal to constant. As A1 is much greater than A2, V1 will be much lesser than V2 as per the equation of continuity. Even if you consider V1 square, that will be even lesser than that of V2 square. So here the term that we are talking about is V1 square by 2. As V1 is small, V1 square is even very small, and this V1 square by 2 we are going to ignore because it's not going to make any significant difference. So when I do that, what's the remaining equation is? GH, I have ignored this term, equal to G of H minus H plus V2 square by 2. So get this term to the other side of the equation, GH minus G of H minus H equal to V2 square by 2. So simplify GH minus GH minus of minus will be plus GH equal to V2 square by 2. So this GH and this GH can be cancelled. That implies G small h equal to V2 square by 2. That implies V2 square equal to 2G small h, which is the height of that opening from the top of the container. That implies velocity of the fluid with which it comes out is root 2gh, as if like a freely falling body that we have learned in mechanics. So the velocity with which it comes out here is root 2gh. That's one important point that we have learned. Okay. We can talk about further like I will do that in the other video, not to make it little lengthy, but let me tell you what I'm going to talk. The fluid that comes out will fall on the floor like this, and from base it will reach somewhere on the ground. That point where it strikes is called range. So in the other video, the next video, I'm going to find out that range of the water drop, fluid drop that came out of it. Of course, I am going to use this derivation that we have made in the other video. Please keep a note of it. I will also calculate what is the maximum of that range in the next video. That's it. Thank you for watching.